Quantum mechanics, the Standard Model and superstring theory are all based on a pre-existing four-dimensional spacetime and are called background-dependent theories. A true quantum theory of gravity must share the basic principle in general relativity that the theory is background-independent, so that four-dimensional spacetime is created as a prediction of the theory and does not pre-exist. Currently only loop quantum gravity, LQG, is a background-independent quantum theory of spacetime. This theory creates spacetime when the separations between points is large compared to the Planck scale of 10 to the minus 33rd centimeter. At the Planck scale, space is simply a collection of points that each has a Planck unit of volume, but instead of the points being connected by space-like intervals, they are connected by relationships that can be thought of as transporting a quantum of Planck area to each point vertex. These relationships define what is called a spin network because the areas can be shown to form a spectrum similar to the angular momentum quantum numbers in atomic physics. Specifically, the area spectrum formula was found to have the specific form A, where L is the Planck length and J is the spin quantum number 1, 2, 3, etc. of the segment connecting each Planck volume vertex point. A small piece of a spin network looks like the figure. The spin network shows that the total area transported to a node is related to the sum of the quantum areas carried by each line segment that intersects the vertex. The segment spins, J, cannot be arbitrary, but have to follow specific rules based on the spin arithmetic developed by Roger Penrose in his related theory of twistors. According to LQG, each spin network represents a specific quantum state of the gravitational field. By encircling a collection of nodes in a spin network, the sum of the nodes generates a specific volume of three-dimensional space, and the segments that pierce this encircled path represent the surface area of the volume. It is the expectation of the LQG program that at very large scales, the discrete formulae that define large spin networks will look increasingly more like the equations we use to define distances in the ordinary three-dimensional space, and which are used as the background for the Standard Model. Spin networks show promise in creating ordinary space starting from a completely non-spatial area. But what about time? The gravitational field is represented by a four-dimensional spacetime, and to get this time-like extension, a succession of spin networks is related to each other by specific moves or alterations in which vertices are connected. The resulting four-dimensional structure of sequentially altered spin networks is called a spin foam.